Hello everybody, this is Cole McClarty speaking, Research Sales Specialist and National Trainer at Transonic Systems. Today we're going to be talking about an introduction into pressure, flow, and pressure volume loop measurement. Before we get started, I think it's always good to take a quick step back and understand who we are. Transonic was established in 1983 and has made itself a world leader in the field of biomedical cardiovascular measurement. Importantly, we operate in both the clinical and the research setting, and specifically we specialize in vascular flow, tubing flow such as isolated heart, ventricular assist device testing, graft material work, microvascular perfusion, which includes things like cerebral perfusion, high-fidelity solid-state pressure catheters, ventricular PV loop systems, and recently biotelemetry, which includes pressure, flow, ECG, temperature, and more. All of these systems go together and allow us to have actually more than 7,000 publications over the past 30 years. Today specifically we're going to be speaking about vascular flow, solid-state catheters, and ventricular pressure volume loop systems. Before we get started with the talk today, I think it's always good, again, to take a little bit of a step back and understand exactly what it is that we're trying to do in a very broad sense. So, in general, people that are going to be listening to an event like this are going to be interested in hemodynamics in general, which is an overarching theme. Pressure volume loops, flow, pressure, telemetry, echocardiography, all of these are just small examples of different modalities that can be used to interrogate hemodynamics. What's important is that all of these different technologies and more need to be able to go together in a cohesive unit to allow us to investigate hemodynamics. Pressure volume loops alone, of course, won't allow us to do that. Flow alone won't either. And so we offer a lot of technologies that are very useful. We partner with other companies that allow us to improve our ability to do so. And then, of course, we also operate with other companies, such as echocardiography is an example of something, of course, that we don't do. But it is an example of something that we do pair synergistically very well with for publication purposes to allow us to view other aspects of research in general. So where we're going to start today is, of course, blood flow. Blood flow is where we started 30 years ago, and today, after several iterations of the system, we've arrived at what we call the 400 series flow meter. So the 400 series flow meter is a paired unit, and what I mean by that is that it comes with the hardware, of course, and the flow probes. So today we're going to be talking about the hardware and also these flow probes that actually go around the vessel to allow us to get a true volume measurement from animals. So what we're looking at here are various different applications. So very commonly when people come to us, they're of course looking to measure blood flow, but specifically because there's so many different applications that we work with, we always need to understand exactly what you're trying to accomplish. So as you're listening to this presentation, you might be thinking about how this applies to your protocols. So an example of an application can be pulmonary artery flow, aortic flow, flow from the carotid. So an example of that would be thrombosis formation. It might be something that you're interested in looking at. Renal artery flow, mesenteric, and more. And so what's important is that we don't just operate in an acute setting. We also, of course, operate with this technology in a chronic setting. So it allows you to pair these different applications depending on your needs. Your needs might be very acute, such as a carotid thrombosis experiment, or maybe renal hypertension is of interest over a period of several months, or it could be you're interested in cardiac output and exercise physiology over a period of several months. So as you're thinking about these technologies, just keep in mind that the application is very broad, and acute and chronic, of course, are two things we specialize in. So typical measurements that can be ascertained from these probes, an example would be cardiac output. If you would put this on the aorta, you also get stroke volume from it. Vascular resistance is an example of how synergistic technologies will go together. So we're going to be talking about pressure later on in this presentation. Pressure and flow, when paired together, allow us to interrogate vascular resistance. Vascular occlusion or thrombosis formation is something that I mentioned with the carotid. Renal blood flow, hepatic and portal metabolism, and the list goes on and on and on. So these are some typical measurements that can be ascertained from this unit. And so before we switch to the next slide, we're going to be talking in the next slide about hardware. What I want you to notice on the front, the top, you can actually see some numbers. In this situation it says 2.55, but that's really irrelevant. What is important is that what that's telling us is the instantaneous flow rate. So it's actually giving us a true volume measurement live on the front of the box. So even before this is paired with the data acquisition system, which we'll talk about in a minute, the system itself will give you information once plugged into a flow probe and around a blood vessel. So you can see in the bottom left-hand corner of that picture an actual connection. And what that is it's a connection with a flow probe, which is what we're going to talk about next. So on this slide, as mentioned in the previous slide, we're going to be talking about the hardware and the probes. The hardware and the probes go together synergistically to allow us to interrogate blood volume flow live. The hardware is called the 400 series meter, and what it's doing is pre-amplifying the signals, sending out information to the probe, but also receiving information from the probe. From there, what it's doing is it's processing the signal and sending it out through what we call standard BNC outputs for convenient software integration. So it allows you to pair with other data acquisition systems. So you can see the flow profile not just on the screen, as I mentioned in the previous slide, on the front of the meter. You can also see it on a computer screen, so you can analyze, save, process the data. And the meter itself will accept our entire line of vascular flow probes and is available in 1, 2, or 3 channels. So the number of channels correlates directly with the number of flow probes you can plug in simultaneously and read flow from. On the bottom right-hand corner of the screen, what you'll see is an example of some of these probes. On the left-hand side of that picture is what we call our nano probe. It's 0.5 millimeters in diameter, and as you move to the right-hand side, we get slightly larger. Now, this is not at all an exhaustive list of what our flow probes look like. There's also what's called a PAU series that allows us to do cardiac output, various other protocols. But this is a small snapshot of what our probes look like. Importantly, all of these probes come pre-calibrated and traceable to NIST. That's true actually of the hardware as well. The reason that's important is that it speaks to the fact that we are able to deliver a product that is ready to use immediately. So it means that it comes to you in a plug-and-play fashion. As soon as you get it, you're able to use it without having to calibrate it anymore. That's a very common theme that's going to come through this presentation for blood flow. The fact that there's no calibration necessary. It's fairly unique to our equipment. And it's something that we're certainly very proud of. Of course, as I mentioned as well, that these probes can be used in both acute and chronic studies. So your protocol might demand an acute setting, your protocol might demand a chronic setting. But luckily we have a probe that will pair very nicely for whatever it is you're looking to do. So I talked about animal models. All animal models, of course, can be serviced by this system. So it's 1 meter and various different other probe sizes that you would then pair with the meter to allow you to do the work, whether it's on a mouse, it's on a dog, it's on a giraffe. And very importantly as well, these probes, although they are very small and appear delicate, they're actually quite robust. So things like cleaning and things like that actually can be done very easily with some warm soapy water and a soft bristle brush. So they're actually a very robust system, and that's more that we'll talk about a little bit later on in the presentation. To understand how this probe system and hardware system is going together to actually give us volume flow information, it's of course important to understand the technologies that's being used. So the technology that we use is called transit time. You might be familiar with another technology called Doppler. What's important, a very common question that will come up is, of course, what's the difference between the two? And what's important to understand is that Doppler is giving you information, of course, that is useful, but it's actually a relative measure. So it's giving you a velocity measurement that is, of course, relative to the environment that you're currently in. What's different about transit time is that it's actually giving you an absolute measurement. So it's giving you true volume live. True volume allows you to then correlate information directly to other animals. And it allows you to make a little bit more powerful conclusions, of course, depending on your protocol. So the way that this works, as you can see in the cartoon image, the probe is designed to go around a blood vessel. It then has 2 transducers on it. So these transducers, of course, are powered by the meter. Sends a signal down to these transducers. What they do is they send out an acoustic signal. It's an ultrasonic signal. And so what it's doing is it's actually bouncing off the reflector in the middle, as you can see in the cartoon image. And it's going back to the other transducer. And you're sending a signal in one direction, and you're sending a signal in the other direction. Of course, as one moves, it's going to be going with the blood flow. And as the other one goes, it's going to be going against the blood flow. As you can imagine, when the signal is moving with the blood flow, it actually moves faster than it will when it's moving against the blood flow. So we're able to do a little bit of math inside of the box, look at the difference between these 2 times, the transit time, and it allows us to derive a very accurate information on volume. And what's important here is that through using wide beam illumination and integration, what's very nice about this technology, it's largely independent of vessel dimensions. So vessel dimensions are still a conversation that you'll always need to have, and understanding, of course, what the vessel size is that you're working with, and because we have various different flow probes, it's important to pair the correct flow probe with the vessel you're using. But what's nice is that there is some flexibility there. So if you're doing a chronic protocol where you're expecting vessel growth, this technology is applicable for that. So it does allow some vessel growth without an impact on accuracy. So it leads to some flexibility, which we'll be talking about in the next slide. And again, as will be a recurring theme, there is no calibration necessary. Get this flow probe around the blood vessel, you will get volume instantaneously. So what does transit flow time provide? I've touched on a couple of these different things, but what it provides is volume flow rate live and instantaneously. So on the right-hand side, what we're looking at is acute cardiac output measurement on the ascending aorta in an anesthetized mouse. So we're looking at full pulsatility. So we're actually able to not just see the blood flow live, we're also able to see the pulsatility of the signal, which allows us to interrogate other additional parameters. There's a very high level of accuracy, so this is one of the most accurate blood flow systems in the world. No calibration necessary, as we've spoken about a few times, and surgical and protocol flexibility. Some more example data we can see here. So what we're looking at is actually blood pressure, which is a topic we're going to be covering very shortly, and blood flow. So the flow, of course, is coming from the 400 series meter, and this is a tracing from the ascending aorta. And it's being measured by what's called a 1.5 PS, and that's just a 1.5 millimeter probe, and it's actually in a chronic implantation, as we can see. So we're talking about 7 days after implantation in a conscious mouse. And we're looking at arterial pressure, which was obtained from a catheter inserted into the abdominal aorta via the femoral artery. So what we're seeing here is two different technologies that are working synergistically to give us important information about what's going on inside of an animal. Importantly, both of these parameters are absolute parameters, meaning that they can be compared directly between animals with a very high level of confidence and a very high level of accuracy. Next, what we're going to do is we're going to move on to blood pressure. Blood pressure, the system that we offer for this is called the SP200. Again, when you're thinking about what you want to do with a pressure system, it's very similar to what you're looking to do with a flow system in the sense that you need to first understand what your application is. So we can work with vessel sizes that are greater than 0.35 millimeters in diameter. So to give you an example of what blood vessels that might entail, we're talking about things like a mouse pulmonary artery, a mouse femoral artery, a mouse carotid. So we're talking about very small vessels that can be catheterized, and then a catheter can be put inside of them to give you an extremely high level of accuracy in a blood pressure setting. So some examples of different arteries or vessels that can be used: of course, the aorta, the carotid, as I mentioned, renal artery, femoral, ventricles, the atria, pulmonary artery, and much more. At this stage, we do, of course, have a biotelemetry system that's not part of this presentation, but broadly speaking, the SP200 is designed as an acute setting. So unlike the flow probes, which are acute and chronic, this blood pressure system is actually predominantly used in acute settings. So you're looking at an anesthetized animal, and you're running a full protocol, whether it would be short, 15-minute protocol where you're looking at femoral pressure, or it could be a dosing protocol where you're looking at 4 or 5 different drug doses over a period of 3 or 4 hours. Typical measurements that people will be taking from the system: systemic pressure, as you might expect, dPdt, which is a very important measure for contractility, a load-dependent measure, which we'll be talking about at the end with pressure volume systems, PA pressures, as we talked about, and vascular resistance, which again brings up that synergy that we talked about in the beginning, where we're looking at pressure and flow together. So this would be an example of how you could use the SP200 and the 400 series flow meter we just spoke about together in a synergistic fashion to derive some additional advanced parameters. So the system itself entails of hardware and, of course, catheters, much like the 400 series is hardware and probes. The job of the hardware is to power the catheter, but also accept information coming back from the catheter, amplify it, process it, and then, of course, send it out to data acquisition systems and software packages so you can actually see the signal live, save it, analyze it, etc. So the SP200 accepts the entire line of pressure catheters. So as you can see in the catheter section, that is from a range of 1.2 French, which is desirable for a mouse, all the way up to a 7 French size. So 7 French would be an example maybe for pig or sheep models, even giraffes, believe it or not. So any large animal and everything in between, we can definitely service to, and they all plug into the SP200 in very standard fashion. So the SP200 itself is a 2-channel system. So it allows you to plug in 2 catheters at the same time. Importantly as well, not really included here in this slide, but important that you should know about, are also what's called dual pressure catheters. So dual pressure catheter is a catheter that actually has 2 different pressure sensors on it. We're going to jump into how pressure is actually recorded on the next slide, but importantly, catheters exist in 1-2 pressure modes, allowing us to look at things like valve research, allowing you to look at things like pulse wave velocity, etc. So we service all animal models, and the tubing materials that we use provide an ideal balance of flexibility and durability, and they're designed for easy insertion and maneuverability within vessels. They also have what's called a recessed pressure sensor, which we'll be talking about in the next slide, and it's something unique to our system. The tip options, specifically for large animal catheters, we can see in the picture here, a mouse catheter on the left. And on the right-hand side, what you see is a larger animal catheter that has what's called a pigtail. You can see that it's got a bit of a hook to it. So when we're talking about tip options, what we're talking about is having a straight tip like you would have with that mouse catheter, or a pigtail tip like you would have with the large animal catheter we can see on the right. A curved tip is something in between. And to understand what tip option is appropriate for you, it's always coming down to what your application is. So for a femoral insertion of a catheter, for example, having a pigtail will help you get the catheter, if your target is going into the LV from the femoral, and it'll actually help it get up and over the aortic arch. Alternatively, using a straight tip is actually much more desirable for an apical insertion or for carotid insertion, because those are more of a straight shot, so to speak. So familiarizing ourselves even further with this equipment, understanding actually how the technology itself works. So these catheters are what's called solid-state catheters. So these are very different from common fluid-filled catheters, which you also might be familiar with, in the sense that what we're looking at is what's called a piezo-resistive element. So this is a solid-state element that bends and flexes dependent on force. So as the blood is exerting a force onto the actual pressure sensor, which you can see in the picture highlighted by the arrow, there's a diving structure, and as it bends and flexes, it sends a resistance or a voltage up the catheter that then can be sensed by the SP200 hardware. What we're doing here is, because it's solid state, what we're able to do is transmit this signal much more reliably than you ever could with a fluid-filled catheter. Fluid-filled catheters operate on the principle that you're still exerting a force in the same fashion, but that force then needs to be transmitted through a fluid medium before it interacts with the sensor. And so that fluid medium can dampen the signal, and it can cause some other issues, which we'll see on the next slide. And so solid-state sensors are certainly the gold standard for absolute accuracy. And so, as I mentioned here on the side, the blood is actually flexing these resistors in the housing. And I also mentioned that what I mean by inside is that actually our pressure sensor is what's called recessed. And so you can see in the catheter picture, looks like there's almost a little bit of a bite taken out of the catheter. There is the sensor itself located inside of that area, and over top of it is a plastic or rubbery material. And so it allows the blood to exert a force onto the element, but of course not interact directly with it. And so because it's actually recessed, what we're able to do is deliver a catheter that is a little bit more impervious to things like motion artifact or interaction with valves, or having anything else touch and create artifact in your signal. And it also improves the lifespan of the catheter. So ultimately, the overarching theme for solid-state sensors is that they are very durable, but also extremely accurate. And relative to any other technology, they really are the gold standard for accuracy. What I'd mentioned on the previous slide is fluid-filled catheters. So this picture is actually showing a reference pressure being applied to a catheter that we make, so our SiSense catheter, solid-state catheter, and a fluid-filled catheter. And so as you can see, the solid-state catheter itself responds beautifully to the reference pressure being applied. But because it's a very high frequency, what you're seeing in the fluid-filled catheter is some reverberations. And so at the very bottom, if you look at the superimposed picture of the SiSense catheter and the fluid-filled catheter, you can notice that there's a lot of noise coming through on a fluid-filled transducer. So the reason that this is important, specifically as you can see in the text at the bottom, anything over 300 beats per minute, which you'd be talking about certainly in a rat, and definitely in a mouse, you're going to be getting these artifacts because the catheter is not able to rest down to 0 again before the next pressure wave comes in. And that's why solid-state sensors are so important for specifically rodent research, but also large animal research, because it has a very high level of sensitivity, optimal frequency response, relatively impervious to motion artifact, and the signal integrity is fantastic. So there's also a large conversation to be had about ease of use as well. Catheter simply needs to be balanced, which you will learn about further, inserted, and the measurement can begin. So it's very simplistic, and of course, as we can see here in this picture, extremely accurate. Here we have some example data coming from the SP200. So it's two different pressure signals, one coming from the femoral artery on the top, and as you can see, it's giving us a relatively normal systemic blood pressure. And you'll notice a much lower pressure on the bottom signal. That's actually because this is coming from the intracranial space of a rat. So this is actually the same animal, two different catheters put in two different locations, but it is showing two different pressure recordings as you would expect, but also extremely high levels of accuracy without any interference. So this is an example of how diverse the catheter it is, but also how accurate it is. The PV loop system that we offer is called the ADV500. Now, unlike pressure and unlike flow, which the technology that's being used in those two systems is relatively understandable and simplistic, a pressure volume system by necessity is a little bit more complex. So we will spend a little bit more time on this section, not because it is necessarily a more important measurement. It might be for your protocol certainly, but it is a little bit more technical. So what we're going to do is we're going to jump into some very specific ideas and very specific technologies, and I'm going to try to make sure that you guys can keep up, because it's very important to understand the technology to then be able to use this type of. So to take a step back, much like the other two systems, first what we want to do is we want to understand the applications that a system like this can be used in. So very obvious settings are going to be the left ventricle, so left ventricular PV loops, which are very common, of course. Right ventricle, which is becoming more common, so right ventricle can be useful for looking at things like pulmonary arterial hypertension. So looking at the RV as it remodels is very useful for that. And also can be used in the atria, which is, of course, much less popular, but still doable. Acute measurements is really the bread and butter for this type of technology. So currently the technology does not exist for chronic applications, but in an acute setting, this is very powerful. We'll get into why it's powerful and why it's useful, of course, but this is predominantly used in an acute prem. Typical measurements that can be ascertained from PV loops are things like cardiac output, stroke volume, properties such as ESPVR. So ESPVR stands for end-systolic pressure-volume loop relationship. EDPVR stands for end-diastolic pressure-volume loop relationship. Those are two complex topics that we're going to touch on at the end. They speak to a very important principle about PV systems, and that's that they are able to give you both load-dependent and load-independent parameters. We'll get to those two concepts, understanding what they are and why they're important. But DPDT is an example of what used to be defined as a gold standard parameter for contractility. DPDT is actually a load-dependent parameter, and what's important is being able to separate load dependency and load independency. So we'll move into that in a minute, but first I think it's important that we understand what the heck a PV loop actually is. So what we can see on the screen here, on the left-hand side, we're looking at left ventricular pressure at the top and left ventricular volume. So it's not typically displayed in this fashion, of course. You're much more commonly will see it in the middle like you will as a PV loop. But on the left-hand side, what it's showing is the pressure changes by themselves and the volume changes by themselves. This is inside of a left ventricle. In the middle, what we're seeing is the two of them put together into a much more familiar PV loop. And so on the right-hand side, it kind of gives us a rundown of what we're looking at. But in general, where I'd like you to start is the bottom right-hand corner of this loop. That's the definition of end diastole. So at that point, we're seeing maximum volume and minimum pressure. From there, we're moving up. So as you can see, the arrows are showing us which way we're going to be going. But from the letter M, we're going to move into the letter B. What that's called is an isovolumic contraction phase. Isovolumic meaning no exchange of volume. So you can see the volume maintains, but pressure increases dramatically. With the letter A, what we're seeing is the aortic valve open. So when we reach a pressure that is great enough to overcome the aortic pressure and open up the aortic valve, what we're getting is a volume exchange. So this is the first point where we're going to be seeing volume exchange. You can see the volume exchange, of course, is moving blood into the aorta and into the systemic circulation, so volume is going down. because the contraction is continuing, pressure itself is mostly maintained. You'll actually notice that it goes up until we reach the end of A. So at the end of the ejection phase. And that's actually called end systole. So end systole is defined at the top left-hand portion of a PV loop. This is minimum volume but maximum pressure, and it is followed by what is called an isovolumic relaxation phase. Much like an isovolumic contraction phase, there's no exchange of volume here, but there is a dramatic decrease in pressure. This is also called tau. From there, we repeat the process where valves are opening, blood is coming back into the LV, and the system, of course, will repeat. So the technology that we employ allows us to look at how these PV loops will change through disease states and through loading states, as we'll get to. But in general, this is a very quick summary of what a PV loop is. Some typical measurements that they report are things like heart rate, maximum pressure, minimum pressure, more familiar things such as, of course, stroke volume and cardiac output, ejection fraction. And then, as I mentioned, also change in pressure over time, so dPdT, which again has been that gold standard measurement for contractility. So as mentioned in the beginning of this segment, it's very important to understand how the technology works with this system. The technology that we employ is called admittance, but there's actually two different technologies that have classically existed for PV loops: conductance and more recently admittance. We actually end up doing both, conductance and admittance, but admittance we view as a more advanced technology. We'll get into the specifics of that in a moment. But to understand how this technology works, you first have to, of course, understand how the heck a catheter is actually getting into the ventricular space. So in this example, we're going to be talking about the left ventricle. As you can see in the schematic, we're looking at the left ventricle. So there's really three different ways to get a catheter into the left ventricle. You can get in through the carotid, which would be the right carotid. You can go in through the femoral artery, or you can go in through the apex. Dependent on what your protocol is, what your animal model is, these are different variables that would dictate which is most appropriate for you. But luckily, the technology works the same regardless of how you get it in there. Technology, what it's doing is there's 4 electrodes on the catheter. The outer 2 most electrodes are putting in a constant current that we dictate, so that's coming from the control box. And 2 inner recording segments, as you can see there in red, are actually sensing how much of the constant current comes back in units of volts. So what we're doing is we're hoping to take that voltage and derive some information from it. We're hoping to derive, of course, volume. So you'll notice on there's a pressure sensor. It's not labeled, but it's very clear in the middle, as we saw in the previous section about pressure. Pressure sensor's there. It uses a solid-state pressure sensor, exactly like a pressure-only catheter. So it's fairly simplistic. So that's where the pressure and pressure volume comes from. The volume, of course, comes from these electrodes, though. The principle is if we can look at the voltage that comes back from this environment, we can convert it into volume using fairly simple algorithms. The thing that confounds this, or the thing that makes it challenging, is that not only does the blood conduct electricity, the myocardium does as well. And the myocardium, of course, because this animal is alive, unlike this picture, it's just static, it's actually beating. So the myocardium is moving. It's actually consuming more or less of that myocardial space, or more or less, sorry, that electric space from the catheter, depending on where we are in the cardiovascular cycle. So to talk a little bit more about that, picture end systole, when you've got minimum volume, myocardium will actually be closest to the catheter, and diastole will actually be furthest away from the catheter. But the current remains the same. The electric field remains the same. So it means that your muscle contribution, how much muscle is there, what proportion of the voltage is muscle, what proportion is volume coming from the blood, actually changes dynamically through the cardiovascular cycle. Changes based on catheter position, changes based on drug study, it changes based on various different things. And so what we're saying here is that it's actually a problem. Classically, it's an issue. How do we get rid of this muscle contribution? So, as I mentioned, there's 2 different technologies. With conductance, which is an older technology, what you're doing is you're actually doing what's called a saline bolus injection. You're injecting hypertonic saline, so very salty solution, highly conductive, much more conductive than the blood, and it will actually radiate or go through the ventricular system after being injected into the jugular transiently, so it washes through after a few beats. And you'll notice on your screen that there is a change in the data. So there's a change in what it's reporting, and that's because the conductive environment has changed dramatically. You're then able to sacrifice the animal, move forward with your protocol, and at the end, post-calibrate your data based on the saline bolus. And what you're hoping to do is come up with a single variable, a single number, a muscle contribution, so to speak. And then you apply that coefficient to your entire data set. And you're essentially saying, I'm getting a voltage of X, and I'm going to delete that from my total voltage, giving me blood voltage only. And then you're able to run through different algorithms, whether using a cuvette or using what's called Bond's equation. You're able to then take that information, run it through your algorithms, and come up with this theoretical blood volume. The challenge is a saline bolus can, of course, only be done at the end of an experiment, so it's not giving you a live readout of what might have happened previous, ectopic beats, drug studies, anything that might have changed in the experiment, such as catheter position. Those all will impact myocardial contribution. It's not telling you that instantaneously, of course. It's telling you how much is there at the end. And as well, the number that it reports can be highly variable. And so ultimately, because the myocardial contribution, of course, is dynamic, as we talked about at the beginning, getting a single number isn't, of course, absolutely accurate. In some settings, it works phenomenally well. And in other settings, it can produce data that does not match other modalities. So we as a company understood these challenges, and actually in the early 2000s came out with a new technology called admittance. As you'll notice, the picture itself hasn't changed. So we haven't changed slides. Everything's the same. Catheter looks the same number of electrodes. We're actually sending in the same current. What's different is what we're actually doing with the data that comes back to the system. So far we've talked about conductance. We've talked about how there's this myocardial contribution that we need to get rid of. We've actually solved that issue and gotten away with, we talked about a cuvette calibration just in passing. We really talked a little bit in detail about the saline bolus and how we can figure out how much muscle contribution is there, because it's a large problem. Admittance addresses that issue head-on by actually looking at what's called the capacitance of the muscle. So the muscle itself has ion channels, and when you pass a constant current through that, it actually will behave differently than the blood. The blood will just simply conduct the electricity, but the myocardium will conduct it, but it also will store some of it, like a battery. And so knowing that principle, it actually changes the signal fundamentally. It actually will shift it. It's called a phase shift, which we'll talk about in a moment. We call it phase. And what it is the difference between the input and the output current directly proportional to how much muscle is there. And so what it means for you is that your surgery remains the same, catheter position remains the same, application protocols, nothing changes. What happens is that the system actually just does more work for you, making your job much easier and making your job much more accurate. And so to talk a little bit about this phase signal, which again is just the muscle contribution, we'll move to the next slide. And so understanding what phase is and why it is important is key to understanding what makes our system unique and what makes our system much more accurate and easy to use. So what we're doing is we're looking at the input and the output current. In this schematic, we're looking at black, which is the input current, and of course the output current is in blue. You'll notice that they're different. And so what I want you to see is that the amplitude is different, so it's not as high, and it has been shifted by units of degrees. And all you really need to take away from this is that the input and the output current are not the same. And the reason that they're not the same is because there's a capacitor present, which is coming from the myocardium. Not from the blood, but only from the myocardium. So to give you two different examples, if there was no myocardium present, your input and your output current wouldn't look like this. They would actually be identical. They would be on top of each other, so you wouldn't see the blue line. If there was nothing but myocardium, you also wouldn't see the blue line, but that's because it would be flat. So there would be no signal coming back at all. Neither of those two environments will ever exist inside of an animal. What will exist is something in between that, depending on various different parameters. But what it's giving you is this difference, and we measure it in what's called units of degrees. And so we're measuring the muscle's contribution to the total signal, which, as I mentioned, is also sometimes called parallel conductance. And it is directly proportional to the total muscle content. So what I mean by directly proportional is the higher the phase shift, which again is just measured in units of degrees, which we'll show you in the next slide, the higher the muscle content. So it varies throughout the cardiovascular cycle. So this brings up another important point. Unlike a saline bolus that will give you a static number for muscle contribution at the end of your experiment, this will actually give you an instantaneous measure from the very beginning to the very end, and we'll be deleting it off live throughout your entire cardiovascular cycle, through protocol states, through disease state, through drug study. Anything that you're doing in your experiment will impact slightly this muscle contribution, and we're able to detect that live, delete it off live, and actually run it through a different algorithm so a proprietary algorithm, and it allows us to give you a much more accurate signal. It's much easier to use, as you can expect, because there's none of these calibration steps, but it's also much more accurate. And so one very important fringe benefit of this is that it also allows for what we call relative catheter position assessment. So in the next slide, I'm going to show you some signals. I'm going to show you what the data coming from the system actually looks like. But keep this idea of relative catheter position assessment in mind, because any PV system, whether it's conductance or whether it's admittance, is position dependent, meaning where the catheter is will in part dictate the volume that's reported regardless of technology. So your job as a researcher is always to get the catheter as close to the middle of the heart as possible. That will allow you to see maximum volume. And that can be very challenging, specifically in small animals, if you don't have some sort of feedback system. So this phase setting is very useful for multiple different reasons. It's telling you how much muscle's there. It's also showing you, relatively speaking, where your catheter is. So let's take a look at that in the next slide. So as mentioned, here's some data coming from the ADV 500 admittance system. And as you can see from the title, the end result is true volume line. And that is unique to the admittance system. But to understand what also makes the system unique, we want to talk about phase, we want to talk about magnitude. So magnitude is something we haven't talked about yet. So looking at signal number 1, which is pressure, and signal number 4, which we call magnitude. Magnitude is your total electric signal. So it actually could be called conductance. So what some people don't understand or realize is that our admittance system is actually also a conductance system in the sense that it reports conductance. Channel 4 is conductance. That's your total signal. So you could do a saline bolus or a cuvette calibration, should you ever want to, with this signal. The reason that people wouldn't do that is that that phase signal we talked about, that thing that allows us to understand the muscle contribution live, it does away with the need to do a saline bolus, as I mentioned. And because what we're doing is then processing it through a different algorithm, you also don't have to do what's called the cuvette calibration anymore. And so what it means is that during your experiment, you get all the data that you would ever want live, meaning you get pressure and volume live. So if we look at these signals a little bit more closely, you'll see that channel number 3 is called phase. And in the previous slide, what we talked about is phase being important for a few different reasons. It's telling you how much muscle contribution is there. It's then, of course, processing that signal, deleting it off your total signal, and then from there, the system is able to give you a volume line. But it's also able to do relative catheter assessment. And as we talked about, that's very important because this technology is position dependent. You do have the onus is on the researcher to make sure that the catheter is as central as possible. And that can be very difficult, specifically in a small animal where you're steering blind. You don't have the aid of fluoroscopy as you might in a larger animal setting. So phase, as phase goes up, so as phase increases, as we mentioned, it's proportional to the amount of muscle you're seeing. So the higher the phase value, the more muscle you're seeing, or the closer you're getting to the muscle, or further away you are getting from the midline. Midline, of course, being the goal. And so what you're trying to do with the system is you're trying to get the phase signal as low as possible. And when you pair that with accurate signals from magnitude and pressure, the system is able to report a very accurate measurement of volume live. And so you as the researcher then are able to make decisions during your experiment. You're able to see stroke volume, cardiac output, and ejection fraction live for the first time ever with a very high level of accuracy because, again, we're measuring instantaneous muscle contribution. We're looking at things live, we're processing things live, and we're sending out things live. So your software will actually show you pressure and volume live. Now, at the beginning of the experiment, or sorry, at the beginning of this presentation, what we talked about is that there's two different things that pressure volume loops are allowing you to see. So far what we've talked about is the technology, which is important for you to understand, but taking a step back, what's very important to understand as a global topic for PV loops is that they're looking at load-dependent data, but also allow us to look at load-independent data. And what I mean by that is there's a principle of Frank Starling's law, which essentially tells you that the vasculature affects the heart and the heart affects the vasculature in a way that one is dictating to the other in certain settings, telling them that they need to change and they need to adapt. And so looking at cardiac output, for example, or DPDT, as I've mentioned throughout this presentation, is very useful, but not definitively indicative of contractility. So classically, people are looking at the PV loops, as you can see on the screen here, They're looking at PV loops because they want to assess complete contractility. They're not necessarily here to look for cardiac output. They're here to look at contractility. And so to do that, what you need to be able to do are called occlusions. So you actually have to change your loading conditions. When you change your loading conditions, you actually change the parameters that we see on the screen. So we're going to move into talking a little bit about these occlusions because they are very important. They're actually what make a PV system unique. One of the only things that make a PV system completely unique. And they allow you to derive what we call advanced parameters. And so these advanced derivatives of PV loops, and this is a very short list, but they include ES-PVR, ED-PVR, so again that's end-systolic pressure-volume loop relationship, and diastolic pressure-volume loop relationship. So talking about ES-PVR, it's a measure of intrinsic contractility or ionotropy. So it's actually looking at how good of a pump is this fundamentally, how good is it at contracting. ED-PVR, on the other hand, is looking at intrinsic relaxation or distensibility or lucitropy. It's looking at how good of a relaxer is this, how distensible is this animal's heart. And you'll see there's two different lines on the screen right now. The top left line is your ES-PVR, so it's defining end systole throughout an occlusion ramp. I guess to take a quick step back so everyone understands how this was derived, what we're doing is we're isolating the IVC. And the IVC is carrying a large portion of the animal's blood. And we're transiently occluding it. Important word being transiently. We're not clamping it off permanently, of course. We're clamping it off over a period of, say, 15 beats. And in a mouse, that's a very short period of time. And what happens is the animal's heart is then allowed to beat intrinsically without loading conditions affecting how it is performing. And as we see these loading changes, we get these different slopes. And as these slopes changes from animal to animal, disease state to disease state, we're able to ascertain a lot of important intrinsic information about the health or the distress of each animal's heart. And so these two parameters are very classically represented in publications, with most reviewers saying that they absolutely need to be there, of course, because this is the only thing, or one of the few things, that report intrinsic properties of the animal's heart. Another thing we, of course, can look at is point 3. This is effective arterial elastance. And so it's a study of the interaction between the heart and the arterial system, so ventricular arterial coupling, and its potential interest in the relationship to your dual pressure studies. We talked about dual pressure studies where we're looking at two different pressure sensors on a catheter, and you sides of a vessel, and you can look at things like pulse wave velocity, but also pressure discrepancies between the two. But ultimately, the key is that there's these advanced derivatives. And they're very important for PV loops because they make PV loops unique. But what is a major takeaway from the technology side is that when doing an occlusion, it actually changes your innate environment. So I'm going to show you that next, and I'm going to talk about why that's so important. When we take a closer look at an occlusion, not just, of course, the pretty occlusion state we saw before and looking at the slopes, but actually looking at the hard data. So looking at how this data has changed throughout the occlusion ramp. What I'd like you to do is look at channel number 3, which is phase, the green channel. You'll notice that at the beginning of our occlusion ramp on the left-hand side, it's going up and down as you'd expect, so it moves throughout the cardiac cycle. As we said, it gets higher at end systole, lower at end diastole. What's important is that as you move through the occlusion ramp and pressure is going down and volume down, volume being channel 2, notice that phase is actually going up. So an animal's heart, if you can picture in your mind a balloon deflating, it's still beating, but it's actually getting smaller. The space is getting smaller. So the overall average amount of muscle in these endpoints is actually increasing. So to talk, kind of to put one further point between the differences between technologies, if you were to look at conductance only, which again is signal number 4 with our admittance system, you would not know if this change is coming just because of blood is decreasing, the actual volume is decreasing, or if it's because something's changing with the muscle. So with the saline bolus again, that's a parameter, an additional step that you'll do at the end, so not in an occlusion ramp. You're not able to ascertain muscle changes in these environments because you can't do a saline bolus in these environments. So with our technology, it's actually the only place you can go to get a live representation of how much muscle is there, which is half the equation, but then we're able to delete it off live. By deleting it off the total signal and processing it through our more advanced algorithm, we're able to give you a much more accurate volume live. And so, again, keeping this global idea of hemodynamics in mind, PV loops are reporting a lot of parameters that you can get in other places. Cardiac output, for example, you can get from our flow probes or an echocardiography machine. DPDT is certainly something you can get from pressure-only catheters. So the question you need to ask yourself is, why are we doing PV loops? This on your screen is why you're doing PV loops. It gives you load-dependent parameters you can get in other areas, but it also gives you this information, load independency, that you cannot get in other areas. PV loops is the only place where you can get this information. And if you're making the decision to use this technology, you have to ask yourself, how accurate is the technology at doing the one thing that it's uniquely good at doing? And in this setting, we can confidently say that this is the most accurate system for doing this type of work because we're able to look at the muscle changes live. If you're not looking at the muscle changes live, what you're doing with your final loops is actually converting muscle volume. If you're not deleting it off live, you're actually not deleting enough muscle off in these environments, which means that your volume isn't accurate, which means your slopes isn't accurate, which means that there's a question mark on why you're doing PV loops in general. Not to put too much of a fine point on it, of course, but that is ultimately these signals is why we are using this more advanced technology. So again, maybe to move back a little further away from this difference between load dependency and load independency and talk about PV loops in general, a very common question is, okay, well, what does it look like? How do I know when the catheter is in a good placement? How do the signals change? And so one thing that we say a lot in the industry is it's a very visual science. So you saw that there's 4 signals on the screen. They're very helpful and very useful for positioning the catheter. But largely speaking, it's a visual process. You will be looking at 2 different axes. So you'll be looking at pressure and volume live, or pressure and total signal live. You'll be seeing how they change as you advance through the aorta. Of course, assuming you're going through the carotid or the femoral. So we'll notice in point 1 that the catheter is inserted into the right carotid or the femoral, as I mentioned, and advance through the aorta into the LV. Notice that the PV loop doesn't really look like a PV loop. It looks incomplete. There seems to be missing the end diastolic phase. There's a kick out at the bottom left-hand side. It doesn't look appropriate. So as we push a little bit further, the pressure sensor and the distal electrodes have entered the heart, and a PV loop begins to take shape. It still doesn't look quite correct, though. So what we would ask you to do is advance a little bit further, which is on the next slide. We'll see that optimal catheter position can be partly monitored through the morphological changes of the PV loop. And what we mean by that is it's a visual science, as I mentioned. And so you can see as things change whether or not you're in a good position. And so we would define this certainly as a good position because we're getting clearly defined end diastole, bottom right-hand corner, clearly defined end systole, and our isovolumic contraction and relaxation phases on the far left and far right are well defined. They're vertical. And so additional feedback can be found through each of the 4 output channels. So as we mentioned, there's pressure, volume, phase, and magnitude. Once you arrive at this relative area, what you would do is then switch over on your screen and look at things like phase. You'd say, okay, is my phase low? I'm expecting it to be low because if I'm in the middle of the heart, it will be low. What does my magnitude look like? What's my volume? You can make all these decisions live. You can move the catheter because there's no post-processing of the signal. You're able to make these decisions live and actually take action before it's too late. And finally, what we've done with this last thing is we've actually inserted the catheter too far. So what we would be getting in this setting, if we stayed here, we're kind of pushing into the apex, we start to get some mechanical PVC, so premature ventricular contractions. You're not really seeing that so much in the signal, but what you're seeing is the isovolumic contraction and relaxation phases change. So they're going from, in the top picture, being very vertical, to in this picture, actually being slanted. So this is just a very quick overview of the things that you can expect to see using this system, but the key being that this is only part of the picture. The signals are also giving you much more information and much more feedback. And when you pair all that together, you're able to get a very powerful system that allows you to pair with other modalities and work synergistically to come up with your ultimate measuring hemodynamics. So to talk a little bit about what Transonic itself brings to the table. As mentioned, we have 30 years in this industry. And so 30 years ago, we pioneered transit time, and ever since, we have been advancing technology further, most recently with the admittance technology for PV loops. And we have thousands and thousands of publications. World-leading technology, and more recently, we brought on a very comprehensive support team. So all the technology that we offer will at one point or another require some level of assistance, whether it is being used by new lab members or whether it has not been used for a couple months because you've been doing other protocols. The point is that you might need help or support. And so relatively recently, a few years ago, we hired Dr. Philip Konechny, who has 10 years of hands-on pressure volume loop and surgical experience. And the services that we include now being led by Dr. Konechny, on-site surgical and system training, on and off-site data support, including webinar assistance for unexpected needs. It's very important. You might find yourself in the lab and you might have a question. We're simply a phone call away. And off-site data review. So these go together to make you feel that you do have a support system, someone that you can call, you have needs. All products are backed by full warranties and satisfaction guarantee. We carry a large stock of catheters, and that's very important. You might find yourself in need of some new products, so lead times are very short, which is unique. And we have a large library of over 100 technical support documents and videos. Of particular note, one that I will mention is our ebook series. So we recently launched a pressure volume loop ebook series, which is 104 pages and covers everything that you would want to know, from the technology that we reviewed very briefly here, through to specific protocols talking about left or right ventricular PD loops, different animal models, surgical care, catheter cleaning, and much, much more. I want to thank you for your attention. I appreciate the time that you guys have spent with me today, and I hope to speak to you again in the future.